Alright, we want to look now at the solving of advanced systems of equations, and you've looked at solving systems of equations in the past, specifically linear systems, and basically there are two ways to solve these, graphically and algebraically. Just to refresh your memory, if I have two lines, and I'm just going to graph these two lines, I know the slope is 2 and the y-intercept is -4, up 2 over 1, up 2 over 1, etc. And this line has a slope of -1 and a y-intercept of 2. So start at 2, drop 1 over 1. When I say that I'm solving the system, what I'm looking for is the point or points that the two relations have in common. And in this case there's one point because we're dealing with two lines, and the point of intersection here is 2, 0. So I've just solved that system graphically by graphing the two and finding the point of intersection. You'll remember that we can also solve systems algebraically through substitution. We could, for example, substitute one equation into the other. So we could put this section, which is equal to y, into this equation to get an equation all in terms of x and solve for that. Another option would be that we could eliminate one of the variables by adding or subtracting the two equations together. Okay, so if I subtracted the two equations, y minus y would be 0, 2x minus -x would be 3x, and subtracting here would be -6. And we could solve it out to get x coordinate of 2, which you can see matches with our graphical solution, and so on. So the point that I'm just trying to refresh in your mind is that to solve a system we can do so graphically and algebraically, and that's exactly what we're going to use when we look at more advanced systems, such as linear quadratic. Now, the only difference that we're getting into now is that we don't necessarily just have two lines, because when we have two lines, you'll remember that there can only be one point of intersection, or if the lines are parallel, no points of intersection, or if the two lines are the same, an infinite number of points of intersection. When we're dealing with a line and a quadratic, remember that a quadratic equation is a parabola, we could get 0 solutions. If this graph just touched the line, which we call tangent, there could be 1 point, or there could be 2 points. Okay, so 0, 1, or 2 points of intersection or solutions. So when you're solving any type of system, you really should be thinking about how many solutions should I expect to get. Alright, let's begin by solving this system graphically. And of course I could always graph by hand, but the problem with graphing by hand is that I need to be very accurate, and unless my points are nice integral values, I'm not likely to find the point of intersection perfectly accurately just by graphing by hand. So I'm going to use technology here. I'm going to use my graphing calculator. I have a line and I have a quadratic. So for the line, I'm just going to isolate y, since I need to do that to enter it into the calculator. -3x minus 9. And the second equation is a parabola, a quadratic, so I'm going to isolate y. Now, we know somewhat what these graphs are going to look like. I've got a line here with a negative slope, so it's going to fall. And I've got a parabola here with a negative coefficient, leading coefficient, so I know the parabola is going to open down. So I'm either going to get no points of intersection, 1 point of intersection if it just touched, or 2 points of intersection. Alright, so let's type these two equations into my calculator. Alright, so I have my equations entered, as you can see, and now I'm going to press graph. So there's the line, negative slope. The parabola is down here, so I can't quite see the points of intersection, so I'm going to need to change my window dimensions. So let's change our window. We need to see lower, so we need to make our y values smaller. Let's maybe go to -30. Okay, I've got points of intersection here. I can't quite see whether I've got 1 or 2. So let's do a box zoom. Zoom, box, and I'm going to put my cursor in the top left corner of where I'd like to draw a box. Press enter. Then I'm going to use my arrow keys just to build a box around the area of intersection that I want to see closer or closely. Let's bring that down a bit. enter, and I can see that I've got 2 points of intersection here and here. So let's use the calculate feature to find those points of intersection. Second function trace. You can see I've got 2 points of intersection in this case. The first curve is the line, enter. The second curve is the parabola, enter. Guess. Now the guess just means they want you to move the cursor to closest to the point of intersection you want to find. So let's find that one, press enter, and 1.04 times 10 to the negative 14th on mine. It might be 0 on yours, but that's basically 0. It's something times 10 to the negative 14th, very close to 0. It's really 0, it's just the calculator's having a bit of a problem finding it. 0, negative 9 is 1 point of intersection. Which isn't too surprising, because if you look over at your equations, those are really the two y-intercepts. They share the same y-intercept, so one of the points of intersection should be the same. So one of the solution sets is 0, negative 9. Now to get the other point of intersection, I'm going to do second function calculate again, number 5 intersect, first curve, second curve, and then guess. I want to move my cursor closest to the other point of intersection, and then press enter. It's turning out to be a nice integral value. 1, negative 12 is the point of intersection. So two solutions. If I plug x and y into either equation, both equations will be satisfied. Both sides will balance out. And so there's my solution found graphically. Alright, so now we're going to look at solving this algebraically. And so I'm going to begin with my equations as they appeared at the beginning. Okay, equation 1 and equation 2. And with a linear quadratic system, probably the easiest method to use is the substitution. And you want to isolate one of the variables in the line, because that's easiest to do. So I'm going to take equation 1 and I'm going to isolate for y, since that's easy to do. Y equals negative 3x minus 9. Alright, so now that I've got y isolated, I'm going to substitute this into here, which is going to give me, so I'm substituting equation 1 into equation 2 in this case, to get 4x squared minus x plus this equals negative 9. And so I have a variable in one equation, a quadratic equation in fact, so I'm going to set it to 0. So 4x squared minus 4x, if I add 9 I get 0, so that equals 0. And so I can factor this, don't need to use the quadratic formula since it factors nicely. 4x comes out, x minus 1 equals 0, so therefore something times something equals 0. X could be 0 or 1, which are the x-coordinates of our points of intersection, which you can see matches what I came up with graphically above. Alright, to get the y values that go with these x values, I'm going to take these values for x and substitute them back into equation 1. Okay, you could do it into either, but you should really alternate equations. So I'm going to substitute into equation 1. So I'm looking up here, I'm going to use this form of equation 1. So my y will be negative 3 times 0 minus 9. So y will be negative 9 in this case. So the point that goes together is 0, negative 9. Or if I plug 1 into the equation, y equals negative 3 times 1 minus 9. Negative 3 minus 9, negative 12. And so the point of intersection is 1, negative 12. Alright, so the substitution method is the primary method you will use when you're doing a linear quadratic system. There are ways you can use elimination as well, but I'll let you explore that on your own. Alright, so now we are looking at a quadratic system, okay, which is basically two parabolas. So if I have two parabolas and I'm trying to find out the points they have in common, in other words where they intersect, how many solutions could I expect? Well, I suppose you could have no solutions. You could have one solution if they just touched there, let's say. You could have two solutions. You could have an infinite number of solutions if the two parabolas were really the same parabola, okay? So 0, 1, 2, or many solutions is possible. So you want to keep that in mind as you're solving. Okay, we're going to go through and solve this algebraically first, and then we'll check it graphically at the end. So when you're solving quadratic systems algebraically, you usually have a little bit more flexibility in terms of the methods you use. If I look at the situation I have here, what I notice is that I have x squareds and I have x's, but I just have y's of power 1. So I'm going to go after eliminating those, the y's that is. And what I'm going to do is I could simply subtract the two equations and the y's will disappear. So 6x squared minus 4x squared is 2x squared. Negative 1x minus negative 4 is positive 3x. Negative y minus negative y is 0. And negative 1 minus negative 6 is 5. And I get myself to an equation in one variable, a quadratic equation, which I know I set to 0 to solve. And then I factor or use the quadratic formula. Of course, we're going to try to factor it first and hope it factors, because that's always faster. If it doesn't factor, then I will have to resort to the quadratic formula. So does it factor? I have 2x and x here, 5 and 1. 1 and 5 are 5 and 1. I have a feeling it's 5 and 1 like that. If I made this negative, I'd have negative 2x plus 5x is 3x. So I have 2x plus 5, x minus 1. Therefore, x is negative 5 over 2, and x equals 1. Alright, so now we want to get the y coordinates that go with those. So let's substitute those values into one of the first two equations. We were using both of them together when we added them, so it doesn't really matter which equation you pick. I'm going to go with number 1. The numbers look a little bit smaller overall. And so I have 6 times negative 5 over 2 squared minus negative 5 over 2 minus y equals negative 1. So that's 6 times 25 over 4 plus 5 over 2 plus 1 equals y. I'm just isolating for y as I do this. This cross reduces to 75 over 2 plus 5 over 2 plus 1. So that's 80 over 2, which is 40, plus 1 is 41. And so one of the points of intersection is negative 5 over 2, 41. And the other one is plugging in x equals 1. Again, back in my original equation. So here we go. 6 times 1 squared minus 1 minus y is negative 1. So that's 6 minus 1 plus 1 equals y, isolating y again, so we get y equals 6. And so the second point of intersection is 1 comma 6. And to solve graphically, we need to have y isolated, so this would be 6x squared minus x plus 1 equals y, and this one would be 4x squared minus 4x plus 6 equals y. Alright, so there we have our equations entered. Alright, so there's our graph. Now we need to be able to see higher. And so I'm going to change my window to, I'm going to change my x's to be a little lower, negative 5 to 5. And I need my y's higher. So let's go to 50. Can we see the points of intersection? Pretty well. There's one here, there's one here. There's two, as we found algebraically. If we do second function intersect, one of them is 1 comma 6, as we solved for, and the other one, that should be close enough for it to find it, negative 2.5 comma 41, as we solved algebraically.